Hi, I'm Jennifer Walker with Sensible Science, here to talk with you about the connection between carbon and climate change. Let's start by considering this beautiful planet we live on, Earth. NASA estimates that there are at least 100 billion planets in our galaxy. And that's just the Milky Way galaxy, mind you. There are lots more galaxies in the universe, but within our home galaxy there are upwards of 100 billion planets. And despite centuries of searching, we have found no reason to believe that a single one of all of those planets is capable of supporting life, especially the amazing variety and complexity of life as we know it. Not one planet except this one, Earth. So really and truly, this planet is special. One of the most important ways in which this third planet from the Sun is special enough to support life is because of its atmosphere. Earth's atmosphere is a layer of gases surrounding the planet, held to it by gravity. The various gases that exist in the atmosphere do a lot of things for us, but one very important thing that they do is to moderate the temperatures we experience at the surface of the planet. This function is called the greenhouse effect. If you've ever visited a greenhouse, you'll probably have immediately noticed that it was a pleasant place to be. Warm but not too hot, and moist but not too damp. That's because the glass walls and ceilings let the sun's energy in, but trap just the right amount of that energy and water vapor inside. Earth's atmosphere does the same sort of thing for the planet. The atmospheric blanket absorbs the sun's energy and keeps it from passing by or just bouncing back into space. That energy spreads warmth over the entire surface of the planet. This is what we call the greenhouse effect. Without the greenhouse effect, the average temperature at the Earth's surface would be much colder, likely a little below 0 degrees Fahrenheit, compared to the actual average temperature today, which is around 57 degrees Fahrenheit. That's a big difference right there. And without the greenhouse effect, the daily and seasonal fluctuations of temperature would also be much, much more extreme. The atmosphere is made up of a lot of different gases and other things as well. Mostly it's made up of nitrogen gas, but there are other gases too, like oxygen, hydrogen, and neon. Not all of the gases in Earth's atmosphere contribute significantly to the greenhouse effect. The ones that do are referred to as greenhouse gases. I'm sure you've heard that term. The most potent greenhouse gases, the ones that absorb the most energy, include water vapor, carbon dioxide, nitrous oxide, methane, and ozone. You might hear all of those mentioned in discussions about the environment and about climate change in particular. They're all important, and they all contribute to climate change in different, interesting ways. But we're going to focus primarily on carbon dioxide for reasons that will make sense as we move forward. For now, I'll just state a couple of important facts about carbon dioxide, which we'll expand on in the next couple of videos. First, carbon dioxide is a powerful greenhouse gas, and its concentration in the atmosphere influences the global temperature. The concentration of carbon dioxide in Earth's atmosphere has been rising since the beginning of the 20th century. And human activities have an effect on the amount of carbon dioxide in Earth's atmosphere. Whenever you see ideas about fixing climate change being discussed on the news or in advertising or social media, you're likely to hear the word carbon, like carbon dioxide, but also decarbonization, carbon markets, carbon farming, carbon neutral. In this lesson, we're going to break down what exactly carbon has to do with climate and how humans are involved. Spoiler alert, it's all about energy. It's often said that plants breathe in carbon dioxide and breathe out oxygen, while we and other animals breathe in oxygen and breathe out carbon dioxide. These two flows of carbon dioxide and energy going in opposite directions are at the heart of how our atmosphere stays balanced. The fundamental processes at work in these flows are photosynthesis and respiration. Photosynthesis and respiration are kind of mirror image twin processes, and they're all about energy. Let's take a look at these processes. Photosynthesis is really about capture. It's the process where plants capture two really important things, carbon and energy. Carbon dioxide is a gas that makes up part of our atmosphere. It's made of carbon and oxygen. Each molecule of carbon dioxide has one carbon atom and two oxygen atoms, which is why it's abbreviated CO2. Green plants take in molecules of carbon dioxide through tiny holes in their leaves and combine them with water or H2O. A water molecule, of course, contains one atom of oxygen and two atoms of hydrogen. The plant uses the carbon, the hydrogen, and some of the oxygen in those molecules to build new, slightly bigger molecules called glucose or sugar. It takes 6 molecules of carbon dioxide and 6 molecules of water to make 1 molecule of glucose. In order to join those 12 molecules together, the plant needs energy, which it gets from sunlight. And by using that energy to build sugars, photosynthesis essentially locks that energy into the sugar molecule. It just so happens that when, during that process, the carbon and hydrogen atoms are used to build the sugar, along with some of the oxygen, the rest of the oxygen atoms aren't needed, so they end up as waste. That's why the plant breathes out the excess oxygen, as oxygen gas, or O2, released back into the air. It's a good thing they do because we need that oxygen, and we'll talk about why in a minute. After photosynthesis is complete, the plant contains that other thing we need, food. Sugar, and the other stuff plants make from sugar, is full of energy. That's why we eat plants, or other animals who have eaten plants, to get that energy. That brings us to what happens when we eat. We need energy to do all the things that we do, like move and think and grow. We eat to get that energy, so we take in that sugar, which is full of energy from the sun, that the plant locked into the molecule during photosynthesis. To release that energy, we use the process of respiration. Respiration is not the same thing as breathing. Breathing is just bringing air in and out of the body so that we can use it for respiration. Respiration is the chemical process of getting energy out of our food. Remember that oxygen was released as a waste product by the plant during photosynthesis? Well, we use that oxygen to essentially reverse photosynthesis and turn that sugar back into its original ingredients, carbon dioxide and energy. We grab that energy, but we don't need the carbon dioxide. That's what breathing's all about, bringing in the oxygen that we need to get energy out of our food and getting rid of the CO2 that gets produced. Inhale, exhale. We use that energy to do our life, and we breathe out the carbon dioxide back into the air where the plant can get it to restart that cycle. Whew! Pretty awesome, huh? Of course, these cycles are full of complicated chemical reactions that we aren't going to learn about in detail here. The big point here is that the capture of carbon and energy in photosynthesis and the release of that carbon and energy in respiration are a mirror image set of processes going on all the time, and they really are what makes life happen. But there's another important part of this. The sugar that is produced in photosynthesis doesn't all go straight into respiration, and it doesn't all stay in sugar form. I mentioned a little earlier that some of it goes into building the plant body. That's really important. Everyone knows that many plants, including huge trees, grow from tiny seeds. Think a little bit about how they do all that growing. Where does the material come from that makes up a huge tree, or a cornstalk, or any other plant? The wood that we use to build things, like most plant parts, is largely made up of carbon, and that carbon comes from the carbon dioxide in air. Plant parts are mostly made up of carbon, and the plant gets the carbon from air. Things that eat plants and things that eat the things that eat plants are mostly made of that same carbon. So, you are essentially built out of air. We just talked about how a plant uses photosynthesis to capture carbon dioxide and make sugar, and about how some of that sugar is used by the plant for energy. But some of it goes another direction. The plant breaks up some of those sugar molecules, combines them with other stuff that it gets from the environment, including minerals and other nutrients from the soil, to build other materials that make up its body. It's important to realize that the carbohydrates, proteins, fats, and other building blocks to make up our bones, skin, organs, and everything that becomes our physical body are built mostly out of the sugar that was made of carbon dioxide in photosynthesis. One other very important element that goes into making protein is nitrogen, and that also is fixed out of air by plants. When we eat plants, we're getting stored energy, plus all of those other things made from sugar to use to build our own bodies. Of course, when we eat meat, we're getting all that same stuff that originally came from plants, concentrated into the body of whatever animal we're eating. So whether we just eat plants or also eat meat, the energy and the bodybuilding blocks we get from our food was all originally captured by the plant, from air. So to sum it all up, our bodies are almost entirely made of upcycled air. And since all of this operates in a big cycle, you probably have molecules in your body that contain carbon that was once exhaled as carbon dioxide by a chicken, a dinosaur, a person, maybe even a person you don't like. It's something to think about. But okay, so that's cool. But what does all this have to do with climate change? Well, as we mentioned in the first video, carbon dioxide is a powerful greenhouse gas. When we exhale it, it goes into the atmosphere. While it's there, it helps the atmosphere keep the Earth cozy and safe, and helps make our planet the perfect place for life to flourish. And since plants are always pulling CO2 back out of the atmosphere to keep trapping energy and making food for us, things should theoretically stay in a nice healthy balance. And they have maintained this amazing perfect balance for the entire history of life on Earth, with some ups and downs. But here's where things get dicey. Respiration, or breathing, isn't the only way that oxygen can be used to release the energy trapped by plants. Combustion, or burning, does this too. And that's why we burn stuff like wood, coal, oil, gas, etc., to get that stored energy out. If you're on a campout and you build a fire, you enjoy that released energy as heat and light. The burning process consumes the wood, turning most of the carbon in it back into carbon dioxide and releasing the energy that was holding it all together. Similarly, you may have noticed that when you put gas in your car, it doesn't last long. As the engine burns the gas, it disappears out the tailpipe as carbon dioxide, and the energy is released and used to make the car go. The energy in that gasoline, just like coal, is a product of ancient photosynthesis. Fossil fuels are called that because the material is made up of the decomposed bodies of plants that have accumulated over the lifespan of Earth. As we burn those fuels to get the energy, we also quickly release all of that carbon dioxide, which is more than the plants on Earth can suck up that quickly in photosynthesis. Not a lot, just a little bit more, but it's causing a little tilt in that balance between CO2 being used by photosynthesis and the CO2 being produced by respiration plus combustion. It's as simple as that. Okay, not really, but kind of. Of course, there's a ton of other complex stuff going on. There are other important processes that produce and consume both oxygen and carbon dioxide. There are other greenhouse gases, and they all have their own interesting dynamics. But that imbalance of carbon dioxide in our atmosphere, driven by the burning of fossil fuels, really is the basis of the whole global warming thing. Before we end this module, I'd like to show you one more thing. This graph, coming from the scientists at NASA, shows the changes in the concentration of carbon dioxide in Earth's atmosphere going back roughly 800,000 years. How scientists were able to determine this sort of information so far back into prehistoric times is a subject for another class, but take a look at the graph. You'll notice that there are big, fairly regular swings. The Earth has experienced large-scale cycles in the balance between these important gases. But look at the part on the right, the last 100 years or so. That spike in carbon dioxide levels is far outside the bounds of the cycles the Earth has ever been through in its history. That spike is the increase in carbon dioxide levels in Earth's atmosphere since humans started burning fossil fuels for energy. I'll leave you to think about that a bit more before we move on to the next module, where we'll talk about how that extra carbon dioxide in the atmosphere actually changes our world.